We saw in the previous topic how to form an image in a plane mirror, the one we're used to looking into. Now we're going to look at some more interesting and different kinds of situations where the mirror or the image forming process isn't quite so straightforward. We're going to be looking at both reflection from mirrors and refraction through lenses. So let's start with what we call a concave mirror, a curved mirror that kind of comes in on itself. You can imagine the reflecting surface from a spoon. That's the inside surface, the surface you'd normally eat from. That's kind of curving in on itself. We're going to use that as our concave mirror. You can see on the image here that we have the curved mirror and 2 points along the axis of that mirror. One of them is labelled C. That's the centre of curvature of the mirror. That's the point that's the same distance from all locations on that mirror surface, like the centre of a circle. There's another point there labelled F, and we'll see in a minute what happens with that point. Let's just go through some general things that would happen if you examined the light that was hitting a mirror like this. A light ray that came in that was parallel to the axis would go straight from reflecting back through that point labelled F. It's obeying the law of reflection at that interface. The incident angle equals the reflected angle, and it travels back through that point labelled F, which you can see we're probably going to call the focal point, because it seems to be where the light is going to be concentrated. A different ray, also travelling parallel to the axis, will go through that same point. That's where the light becomes focused. Now, strictly speaking, this is only true if our mirror shape is a parabola. But for distances not too far off the axis, it also works for spherical mirrors. And we call this the paraxial approximation. You can see if we turned this diagram around and put a light source at the focus, then the rays from it that struck the mirror would all come out parallel to the axis. And that's in fact the kind of thing you see behind a headlight, where you want all the light to come out in some kind of beam. The other ray we're going to look at in this mirror is a ray that comes through the centre of curvature. Now, it will arrive at the mirror at right angles to the mirror. It's basically following a diameter. And that means the law of reflection says it will be reflected exactly back along the same direction it came from. Now let's see how using these rays can help us understand images formed in these mirrors. So we'll take our concave mirror and we'll place an object out in front of it. Again, this red arrow. And we'll think about the various light rays that might be coming from the point of that arrow. And again, we'll consider two that help us a lot. We'll consider the one that's parallel to the axis. When it strikes the mirror, as we saw, it will come back through that focal point. And we'll consider the ray that goes through the centre of curvature of the mirror. And again, when it strikes the mirror, it's reflected back upon itself. Now, where those two rays cross over, that's where the image will form. And we can see in this example here, that image is going to form right about here where those 2 points, those two rays intersect. So we would expect to see an image at that location right there. Now, there's a couple of things to note about this image. The first one, that's maybe the most obvious, is it's upside down. We call that an inverted image. The object was pointing up, the image is pointing down. It's also reduced. It's not magnified to be larger, it's not the same size, it's actually smaller. The other thing that makes it a bit different from the image we saw before is this is what we call a real image. It's called a real image rather than a virtual image because it is formed where light rays actually overlap, rather than having to trace back the light to see where it looked like it came from. Now let's see if that's the only way we can use a convex mirror. A concave mirror. What if we put our object a little bit closer, now inside the focal length from the mirror? We'll use the same approach using similar rays. Here's the one that's parallel to the axis. It comes back through the focus. And because of course we're already inside the centre of curvature, we can think about the direction a ray would travel to come through the centre of curvature, and it will hit the mirror again at right angles to the mirror, and so it will be reflected back upon itself. Now once again we have the situation where these two rays coming off the mirror, one in that direction and one out in that direction, they're diverging. They don't overlap. So it might look like once more there's no image being formed, but again we trace them back to the point where it looks like they come from, behind the mirror surface. And that point again is where the image will form, at this location here. And so for that arrow as the object, we would get an image located right there. It's a little similar to the plane mirror in that the image is behind the mirror surface. Once again, it's a virtual image, but this time it's actually magnified. It's also upright. Now you can actually try these two kinds of concave mirror image forming yourself. If again you just find yourself a nice curved spoon, if you hold that spoon and look at your image, you'll see when it's a long way away, you'll see the image like we described before. That is an inverted image in the spoon, and it's slightly reduced. As you bring it closer and closer to your eye, if you get it right up close to your eye and there's enough light coming in from behind, you'll actually see an enlarged virtual image of your eyeball. It's actually quite amazing. Now, let's try a different shape. Let's try, if you like, the other side of the spoon, the convex side of the spoon. If we go to the convex side of the spoon, we've now got our focal point and our centre of curvature still on the inside of the curve, because that's where it makes sense, but our reflecting surface is on the outside. Let's place an object here and consider a ray parallel to the axis. It again will reflect off as if it was going through the focal point, and so we could trace it back. That's the direction it's going in to obey the law of reflection. And the ray that goes through the centre, or would go through the centre of curvature, it of course gets reflected back upon itself. Once more, you can see the rays leaving the mirror are diverging. That tells us we have to trace them back. In fact, in this diagram, we've already traced them back. And you can see this is the point here where the image will form. Once more, it's a virtual image. Again, in this case, it's reduced. It's behind the mirror, that means it's virtual, and it's upright. And again, just take that spoon, turn it around and look in the convex side of it, and you'll see exactly that kind of image. Now let's move on and see what we can do with a lens, where instead of reflecting the light, we're going to refract the light. So that blue object in the centre of the screen, that's an image trying to represent a curved glass surface that might form a lens. And when the light rays from our object here travel, for example, parallel to the axis, they won't get reflected, they'll be transmitted. And parallel means we actually go through the focal length of this particular lens. The other ray that's quite useful is one that goes exactly through the centre of the lens. In this case, it doesn't get deviated at all. And where those two rays overlap, one more time, is where we will get an image. So we can put our image there. In this instance, it's again a real image. Those two light rays actually overlapped. It's inverted, and although it's hard to tell, it's actually slightly magnified in this case. Now, you can practice with soup spoons. You can maybe even find a magnifying glass around somewhere and practice and see if you can form images like this. In the next topic, we're going to combine some of these elements to make more useful optical instruments.